what makes it fundamentally different from every other advanced reactor on the drawing board today that we're seeing?
Yeah, that was a complex question with all the technical details, but I'll try my best. So the first thing you have to recognize is that the majority of nuclear reactors that we humans have ever built are made out of fuel rods, so essentially long cylinders inside a reactor core that is also a cylinder. So it's cylinders and cylinders, and we sort of we realized that we cannot get the performance we want with that old model of cylinders and cylinders. And the reason why they started like that is just because it was easy to calculate in the 50s and 60s when they didn't have computers. It was easy to calculate on a piece of paper, and then also it's easier to manufacture. So that's why we started there, and I think that's a reasonable, good idea to start with that solution. But it turns out that if you want a high performance nuclear reactor, it's a bad idea to have cylinders and cylinders, and this is why we invented the onion core, which is sort of an onion with many layers on top of each other. So that's one thing, and by doing that, we were able. And okay, another thing is that most of these reactors that other companies are building, they run at high pressure, so very high pressure inside the reactor, and that makes everything super expensive. If you look at other industries where you need to run at high pressure, everything gets expensive because suddenly you need licensed components, and especially if it's high pressure and radioactive, then you need super duper lots of tests and licenses and certifications on the steel and whatnot. But with molten salt reactors, you don't need to run at pressure, and also it doesn't need to be very big, whereas classical reactors are always very large. They are typically 10 meters tall and so on. But with our reactor, this onion core that I talked about before, it's like a giant ball, and it has 2.5 meters in diameter. So it fits inside a regular shipping container. And then, of course, you need to put some other things in there as well, heat exchangers and pumps and some electronics and measurements and so on. But it all fits nicely inside a 40-foot shipping container, which is easy to transport on the road. And it's also easy. It's an easy, nice size for mass manufacturing. So of course that's why we chose that, because it lends itself to mass manufacturing, just like, for example, cars in a car factory. So that's the reason why we chose that size, and it's actually the onion core. When you have that size between, well, it depends a little bit on the configuration, but between 2 meters up to 2.5 meters, that's the most optimal size seen from physics. So if you try to make it bigger, you might be able to get more energy out, but it's less efficient. So it's actually better to build two next to each other instead of making it bigger. And the analogy to that is also, people say, but why don't you just build it like super big, 20 meters in diameter? Because it would have super bad efficiency at that size. And the analog is, if you look at computer chips, I mean, when we need a giant computer, we don't build a computer chip that is 20 by 20 meters. We still build many, like millions of small chips, and then we put them in a data center and put lots of them next to each other. And this also gives redundancy, because if one of the computers boot or goes bad, you can still run the data center. It's the same with these reactors, that they are most efficient at that size of 2.5 meters roughly. And then you can just put many of them next to each other. So that's also what we plan to do for nuclear power plants. We plan to put 10 or 20 or 100 units next to each other, depending on the size of the power plant. And this also enables you to sort of slowly build up the output of your power plant. So you don't need to build the whole thing from day one. You can start with less financial cost and get it up and running, and then once you've shown that it's running, then you can always extend it and put more and more units.
Amazing. You have already built multiple full-scale prototypes and hit some impressive testing milestones, including 2 years of continuous molten salt pump operation. Walk us through the development progress. Are you happy with the design you have for the reactor? You're very confident that this is it, and you're ready, and you want to do the 2028 criticality and really push for that, mass manufacturing, maybe do the first customer or client and then go from there? Is that the plan? Is that where you're at?
Yes, so the current R&D center we have here in Copenhagen, we have enough space to test 5 full-scale reactors next to each other. We're not allowed to turn on the chain reaction here in Copenhagen, but we can do a lot of other testing where we just heat up the salt with the electricity and pump it around and do all the testing that is required here. And then eventually we will take one of them and bring it to Switzerland and turn it on there once we have the license to start the chain reaction there. But they are sort of super easy. I mean, we can just put them on a truck here and drive them over to Switzerland, and then we can run the test there and drive them back again and so on. So it's much easier than this traditional nuclear reactors that takes 5 years to build. And you have, in some of those, you have 2,000 workers, making steel and concrete every day for 5 years. I mean, this is just what we are building is a completely different story. We order components from suppliers locally or even sometimes far away, and then all the components arrive here, and then we assemble the reactor, and that takes like half a year. We've done that, like you said, a couple of times. We have 2 units running now, and we're building the 3rd one now. And of course, there are minor changes from one to the next, where we're learning some things could be better if they're changed. But in general, they are all based on the same design with the onion core and the same pumps and so on. And those are already running here. We are testing every day, and as we get more and more units, we will be able to test more and more. And I think it's amazing because if you look at some of the other nuclear companies around the world, even sort of very large nuclear companies, none of them have a possibility of putting 5 reactors at their R&D center just for testing. So that also tells you that these reactors are much more small and nimble and easy to build than the traditional reactors. And even the other advanced reactor companies, even some of the ones in the US that got a lot of funding, even they do not have 2 reactors up and running already and possibility of building 5 units at their test facility. So this is great. And the next thing with this facility we have here, it's a quite large factory we're working at. Here at this facility, we can also build the first 10 commercial reactors, and we can also build the fuel for the first 10 or 20 or 50 reactors. So the production facility here is already big enough to sort of get off the ground. It's not big enough to make a gigafactory and sort of make one reactor every day, but at least we can get off the ground and make the first 10 or 20 nuclear reactors, commercial nuclear reactors, and all the fuel needed for those. And then once we've done that and shown that it works, then of course we will build a gigafactory somewhere.
That's what's exciting about Copenhagen Atomics is that when you're talking with, the hyperscalers, the institutional investors, the big giants that want to work with a partner, you've already well ahead of all of these companies that you just mentioned, and you're already set up, and you can do the first 10, and that's pretty massive, and that's incredible. I'm curious. Talk to me about your kind of designs and thinking around the safety features of your reactor, whether it's shutdowns or maintenance or the things that you work on to kind of keep it generating energy, and also your spent fuel, and how do you manage that? If you can just talk through those.
Yes. So I want to maybe start with the spent fuel, because that's also one of the things that got me very excited in the beginning, because we realized that we can use the fuel from light water reactors. All the other reactors in the world today, they run the fuel for some amount of time, and they don't use all the energy in the fuel.